All right, thank you everybody for the seminar from one of our own students, right? So, and he was kind enough to drag along a couple of other people with him. So we have Dr. Jonathan Förste with us as well. He's also going to be talking. And well, I'm just going to hand it over to Usman. He's going to, I'll request him to introduce his work and then go ahead.
Okay,
Thank you, Usman.
Thank you, Dr. Rizwan. Hi, assalamu alaikum. I am Usman. I am from the batch of 2021, and I have just finished my master's in Germany at the University of Munich, and I will talk about my master's project today in this seminar. I'm very grateful to Dr. Rizwan for organizing and hosting us. I'm joined with Jonathan, who's also my colleague from LMU, and Francie, who's also my colleague. And later on, Jonathan will also present what he does at the university in his company. But first, let me start with talking about my work. My master's project is about fiber cavities, which is a special type of a Fabry Perot resonator. I worked with this company called Colibri. It's a startup inside of LMU. So it's in the umbrella of the chair of Professor Hensch, who is a Nobel laureate in 2005 or 2004, I think. The Colibri specializes in producing these fiber-based resonators, and my project was about making a new product in the company. So I will be very basic and broad so that we can go into specifics if anyone is interested in discussing. So what are optical cavities in general? An optical cavity is the volume between two highly reflective surfaces. So if you imagine two surfaces and you send in light through one side, a fraction of that light enters this volume, and then the light bounces back and forth according to how much reflectivity there is, and then a fraction of that light emits on the other side. And if you think about the wave version of light, and then you can think of these as standing waves of light, which should follow this resonance condition, which is a half integer of the wavelength. It should be equal to the length of the cavity. And so only at these lengths should you see a resonance, and vice versa. At a particular length, only certain wavelengths should emit light or produce light inside the cavity. So if you were to plot this as a function of frequency or wavelength, you should see these resonances at certain frequencies only. And these resonances are actually not lines, rather they are a bit of a Lorentzian curve because of the limited reflectivity of the mirrors. And the space between two resonances is called the free spectral range of your resonator. And if you take the fraction of the free spectral range with the width of this Lorentzian, and the line width of this Lorentzian, you should get what is called the finesse of the cavity. And this is a very important measure of the quality of your resonator. And it tells you about the number of round trips of light that the particle of light takes, the photon takes inside the resonator. So this is the basics of optical cavity. But what are fiber optical cavities? So a fiber optical cavity is when you make this mirror on the end facet of an optical fiber. So what we will do, and I will explain this in detail, that we basically use laser ablation to produce these concavities on the end facet of the fiber, and then we apply a reflective coating on the end facet to produce these mirrors. So how does this happen? Well, optical fibers, as you know, they are used widely in the world right now for telecommunication and other applications. Colibri takes certain optical fibers according to the requirement, and then we take these, we cut them, we basically cleave them, what is called cleaving. We basically make really flat, the end of the fiber, we make it really, really flat. And then we shine a very high-powered laser onto the end facet to evaporate away the material at the end facet. And the goal is to make these concavities at the end facet that should look something like this on a white light interferometer, or if you want to see like a 2D depth map, then you can also see it like this. The idea is to make what is spherical on this side, but actually Gaussian, if you look at it like this, concavities on the end facets. So this is the optical fiber, and I should do it here. This is the optical fiber, and this is the core of the fiber, which is actually the waveguide of the fiber. And you want to try to ablate or evaporate away such that the minimum of this concavity is actually at the core, so that when you send light in through, you should be able to couple it into the cavity. And then in the end, the last step is to apply a highly reflective coating to make it into a mirror. So Bragg reflective coatings are designed by Colibri, and they're designed according to the specification, what you need, and they can be reflective according to what the customer needs, because the Colibri is a startup that sells to people. So we have customer requirements. So according to the customer needs, we design these coatings that are reflective in certain bands, and then externally we get them coated such that this reflective coating is applied on the surface, and now the mirror is ready. So we had the fiber, we ablated it, and then we applied the coating, and then now you have a mirror. And now if you imagine, if you put two of these fibers against each other, facing each other, now you have the two reflective surfaces facing each other. And now you can send light in through either of the sides and form a cavity between these two fibers, and then transmit it on the other side. My project was about this, but I will very quickly show a video of what Colibri does with these fibers. So they don't use two fibers, but they use one fiber and a large mirror on the other side. And then this thing is used as a microscope. So I can show it in a nice video right here. So if you imagine you have one of these fibers and you have a large mirror with a similar coating on the other side. And if you send light in through one side, so if you have a sample in the middle that is very weakly interacting with light, you send in light from the fiber, and if the light bounces back and forth, at every round trip of the light, it will scatter or absorb a bit of the light. If it's weakly interacting, then it will not scatter much on one round trip. But if you imagine like 100,000 round trips of light, then at some the contrast increases a lot, because there's 100,000 times enhancement of the scattering. And so if you have many samples on the mirror and you compare the absorption or the transmission of light compare the transmission of light to a point where there is no sample versus where there is a sample, you can make a whole image of your sample on the mirror, and you can look at the transmission. So this is basically absorption spectroscopy of your sample that you can do. So this is what Colibri already does, but my project was about producing a new product, making a new product using two fibers, which was basically like this. This was the idea. You have two fibers with two mirrors facing each other, and make a product out of this and see if this is commercially viable, if we can make it, and we can set according to the customer's requirements. And what is the point of having a fiber fabric resonator like this? Well, the idea is that the light field between the two mirrors is a Gaussian, and the waist of the Gaussian is a very small area. If you were to have a sample at the waist can get very small, up to nanometers according to the wavelength of light, the Rayleigh length of the Gaussian beam. And this is very important because the volume of the light field gets really small, so the concentration of the light field gets very high in this area. So if you want a very strong interaction, a strong coupling with your whatever sample you have, you can get that because of the size of the mode volume. And the other thing is that as opposed to monolithic cavities, which are inside of a solid state system, this is an open access cavity. There's nothing going on in the middle. So if you want to send in a beam, if you want to trap something in the middle, if you want to send in a fluid in the middle, you can easily do it. The light field of the resonator is open access. And the third thing is also very important, which is the fact that these fibers are micrometers in thickness. They're very small. You can't even see it unless you see it from like an arm's length. And this is very important because then you can integrate this into a very bulky system. If you have a much bulkier trap or hardware going around, you can easily integrate it into it and not have trouble with that, as opposed to larger cavities, which are like made of larger micromirrors. So what are these used for? Very quickly, so one of the applications is that you can detect fluids in this cavity. If you have a fluid going through the volume of the cavity, the light field gets scattered, perturbed, and then you can see those changes in the transmission of the cavity. And this is a paper that's very interesting. They actually were able to resolve individual molecules of individual solution phase molecules, using the fact that when a molecule goes through the cavity, the effective length of the cavity changes, the optical path length of the cavity changes, and then you can actually see the cavity sort of goes out of lock. I'll explain what locking is, but the length of the cavity changes, the optical length of the cavity changes, and you can actually resolve for individual particles with this.
So how sensitive is this? Because I know somebody in LAMS is doing work on detecting impurities in milk, for example. Would this work for that?
Impurities in what? Sorry?
Milk.
Milk. I will have to look into this.
They're using optical methods, by the way.
Okay.
So you might want to talk with them.
But is it like absorption?
I don't know. I don't really know the details. It's some optical method that they're using. That much I know.
And can they give me something that I can just use at my home to test them out?
Exactly.
The guy that's delivering my product. Yeah? That's what I care about.
I mean, that would be a commercial product that you could make out of it, like detection of impurities in air, or I mean, you can basically, the idea is that you can tune it, right? So even if you have a fluid inside of another fluid, you can tune it according to the absorption of one fluid. So I think in theory you should be able to detect individual particles of other impurities, but I'm not sure about this particular.
Yeah, because you have to filter it as well, right? In the sense that, of course, there will be some impurities.
Yeah, sure.
I mean, no buffalo or cow is good.
Pure milk, yeah.
Should be detecting the particle of size nanometer, right?
Yes,
Yeah.
definitely. I mean, the
You
size.
can make it bigger as well. You can make it to detect bigger particles as well.
I mean, the bigger it is, the more scattering it has. So then the light field gets perturbed too much also. So because it depends on the finesse of the cavity. If you have too many round trips, then the scattering amplifies by that much. So if you have a very highly scattering particle inside, and then the light is already moving 100,000 times, and at some point you won't even see any transmission of the light. So this is also important. Let me just check the battery of my laptop because
Charging.
no, but that's that laptop.
Oh.
Just a second. Okay, well, let's just hope it's charging, otherwise it dies out, and then
We'll find out.
Okay, we will find out. Another thing is strong light matter coupling. This was one of the most important applications in any quantum network. In many quantum networks, you need these nodes, for example, but also in other applications where you want to have an emitter of any sort, and you need to Purcell enhance the transmission, and you also need to have a pump into the emitter. So you need to. So you can basically, first of all, Purcell enhance it, and second of all, you have an inherently fiber coupled system. So you don't need to worry about aligning the stuff. You can just send the light into the fiber, and you can pump your system. You can also detect your system. And what I mentioned before, that the fact that it's open access is that you can put it inside of a trap. So if you have an ion trap or atom trap, you can. In this case, it's an ion trap. You can put it inside of that, and you can measure your transmission of your. And also the idea is that because of the highly reflectivities, you can have really narrow line widths. So even if you have multiple transmission spectra, multiple transmission lines of your emitter, you can filter out exactly which one you want to measure according to the tunability. The tunability of the system is very easy. And the third is a very simple application, basically a spectral filter. You have boundary conditions, you have only certain wavelengths of light that can fit in, so you can just make a simple spectral filter out of it. And the simple point of that is that it's tunable. So you can, because of just by changing the size of the resonator, you can change which wavelength it will transmit or reflect according to the requirements. So this is the point of getting them made. What would people need it for? But my project was about designing a fully tunable, ultra stable, and open access Fabry Perot cavity mount. So the idea is not to make the fibers. The idea is to make a mount that will hold the fibers, and then it can be used in my laptop died. Sorry, I don't know. Whether this thing wasn't on. Apologies.
Saw some light.
Now it's on. Just do 1 minute.
So any question?
Any questions? That's okay now.
Good time to stop for questions.
Yes.
What is the basically resolution of these cavities? Like if you are making such a narrow cavity, the resolution what is the frequency at which it can resolve? Like if if there is a molecule which emit different line like 100 gigahertz and 50 gigahertz, whether it will differentiate between that because the length is too small.
If the length determines your transmission condition, resonance condition, and the reflectivity of the mirrors will tell you whether you will form a cavity or not in the first place. And we do have certain mirrors that have dual reflectivity. So, for example, one of the most common one is 780 nanometers and then 1550 nanometers. Our customers need them the most. And so you can form a cavity that can reflect in both at the same time, depending on your use. A lot of times our customers use one wavelength to lock the cavity. I will talk about locking in a second, and the other one to measure the sample.
And the resolution you can tune by the reflectivity of the cavity, right? Like this is the coating on top of the fiber.
Yes.
So sometimes you need like a broader spectrum.
Yes.
Then you just make a less reflective coating. And with a really high
the coating, not the length, because you can also
I mean the length is
Sorry.
Okay.
Good.
Determines the resonance condition, right? But the finesse is determined mostly together with the length, but mostly by the reflectivity.
What is the reflectivity by all these fiber?
I mean, I had a graph there, but it's like million parts per million. So I can show you the chart that I showed before. Yeah, so it can go down to 10 to the -4 transmission, 10 to the 4 transmission parts per million. It's nice. If you can think about it in percentage, it's like 99.999% reflectivity. But the reflectivity is customized. So sometimes you need lower, as you mentioned, depending on the line width that you need. This line that I showed before, this depends on how much reflectivity is there. If you need lower finesse, as Professor mentioned, if you need lower finesse, then you may need a lower reflectivity.
So it means if I want to use for like 550 and then for 750,
Mm-hmm.
it means I have to change the reflectivity or change the cavity. Or it is in the fibers, you cannot change the length or it's the reflectivity. So you need different fiber cavities for them, like for to work with one and to work with another.
I mean, if they're integers are multiple of each other, then you can use them at the same time. But otherwise, yes, you need different lengths for them.
You said that your work is based on making the mount for that rather than the cavity.
Yes.
But what is the mount over here? This
In this?
yeah, which part in your optical fiber? You mean that what is holding these?
Yes, exactly.
So what is the challenge in that?
Oh, I'm going to come to that. That's the whole talk afterwards.
Just a quick question. Are we still recording?
Yeah, that laptop is recording, so I'm fine. Okay. Yeah. So the idea is to build a mount, as you mentioned, but the mount is a product. It should be a product. So this is not a new thing. Of course, people have made these and they've used them in specific experiments, but we need to make a commercial product out of it, like commercial for labs to use them, because QLibri already makes a fiber planar mount and we sell the whole system. So this would be an idea to sell this whole system as well, with all the electronics, controls, everything in it. So I will quickly get to the mount part. So there are many requirements. I won't go in detail, but for example, you might need large lengths of your system to allow inlets for gas sensing, for example. You may need to tune a lot of your cavities, or how much change should you allow the fibers to have against each other. You might need really high transmission in, for example, optical filters. If you have a very faint signal, if you attenuate most of it, then there's no point in having a filter like that. And you may, I will talk about stability, but you may need like high picometer level stability, and you may need high vacuum compatibility. So there's a lot of requirements, but my project was about prototyping it. Just make it once, see if it works, what are the challenges, and then see if we can make a product out of it, but depending on the customer requirements. So I'm muted actually. Sorry, camera. So there are many attempts people have done. I will go very quickly on these because we might not have enough time. Yeah, so this is one example where people have made these custom mounts on ceramic. They put the fiber, one fiber is right here, the other one is right here, and they meet in the middle, and they have piezoelectric actuators underneath these mounts to align the two fibers. The main trouble with the mount part, as you mentioned, was alignment of the two fibers. They need to face each other and they need to be perpendicular to each other. And they're micrometer size, so there are a lot of challenges in how to do that. Any sort of misalignment can cause loss in the light field inside the cavity. So one idea was this group in Bonn that made this. They had these actuators and mounts. Then there was this group in Vienna who had these, if you can see them, they're ferrules. So they're tubes, basically. Ferrule is a tube that you can put the fiber inside, and then they glue that tube onto a platform with alignment as well. So you have good accessibility, but then you cannot tune it because you've glued the thing onto the actuator, the ferrule onto the actuator. And once you have glued it, that you can't change it. So you can't even realign if you need to. So we did not want to go for this approach either. This is in Innsbruck. This is the Nordhook group, and they are using it for ion traps. So they needed to have these complicated lever systems and adjustments and stuff. But the cost is of stability, because you have so many levers everywhere that you may just have a lot of vibration and instability in the system. In this case, they were able to actually achieve good stability, but then this is a complicated system, and we may want to start simple first. And this is a very old one. This is Jakob Reichel. He actually had a patent for this. He put the two fibers inside of a glass box and then had a patent on the welding mechanism. And then he has an inlet here, if you can see it, for the fluid to go in. So he's measuring a fluid inside this glass box. But then once you weld the fibers, you cannot tune them. You cannot move them around. So you cannot change the length of the fibers. And then last is this group in Karlsruhe, David Hunger. He is also the pioneer for this ablation method, where you shine this laser onto the fiber and then you can have this concavity. And what they're doing here is they have a glass box. This is called a glass ferrule, a single glass ferrule. And there's this guiding bore into the ferrule. You can see it on the image and also in the diagram. The two fibers, one fiber will come from this side, will come from this side. And then they have also drilled holes on the either side to get inlets for the whatever measurement fluid they're measuring. In this case, silicon dioxide spheres. Whatever you want to measure, you want to have inlets for this. And they have high vibrational drift stability. And because everything is inside single ferrule, so you don't need to worry about transverse degrees of freedom. Everything is passively aligned. Everything is already, you just need to put the fibers into the box. But you need to drill a hole to get to the actual volume. So you may have limited access. And because everything is passively aligned, you cannot change the angle. So while it's easy to do that, but then you need the profiles, the ablation profiles, the concavities that I mentioned to be centered. They need to face each other. And if you have a little bit of mismatch, the fibers will face each other, but the ablation profiles don't want to face each other. Then you need some degree of freedom to make them face each other. So this is something that we went for. This was the approach we took. And
how is the tunability here? How does that work?
So you can externally have an actuator outside of the fiber, and you can then pull the fiber or push the fiber as you need to. The fiber is guided by the glass box.
Okay. And that is not going to affect the vibrational stability of it.
I mean, that's the challenge. How is your actuator working then? Is it a piezo-based system? Is it a motor-based system? So that's one of the things that I will also see in my system.
Okay.
But the thing is, one thing I mentioned, I mean, spoiler alert, but something I measured was that because the fiber has a protective coating as well outside, when we prepare the fibers, we actually chemically evaporate or dissolve the protective coating. But some of that dissolving part is imperfect. So you may have a bit of material stuck on the outside. So the fiber radius increases at some point. And this actually leads to the fiber sticking inside the core. So then even if you don't have a good stable system, the fiber still has a bit of a friction in the system, and then it may be actually accidentally stable. But there's something I measured in my system afterwards. So this is the basic idea. I have two fibers. I've drawn a cartoon here for that. And just to reference, this is the fiber cladding or the glass bit, and this is the core bit of the fiber, the refractive bit. And the light field inside the cavity is this Gaussian, and we will put this inside a glass box. So it'll all be guided indirectly. And here's an image of that, if it loads. Actually, this is a video, but I could not find the video file in my server, and so you just have to work with the image. But let me just show you. This is one fiber coming here, this one, and this is the other fiber. And this whole thing is the glass box. And the cavity is made between the two fibers right here. Let me point with my mouse as well for the online audience. Right here, this is the cavity. This is actually a video. I also show the fiber moving back, but I could not find the video file in my server right now. This is a microscopic image. So this is this thing is about 130 microns, and this is about less than a millimeter, or 1 millimeter almost. This whole thing. So let's see what we measured. The first thing we do is to form a cavity. We send a broad spectrum light, white light is what is referred to, and we send it in, and then we adjust the cavity length and check the spectrum on the other side to see what wavelengths of light are transmitted. And in principle, what should happen is that you should have only certain wavelengths of light that should transmit. So you should only see certain peaks, as I mentioned before in the second slide. And that's what I see. This is my transmission spectrum. You see, so I will explain. You see no transmission, then no transmission. Please ignore these peaks for a second. Then transmission, and then transmission. And these higher order peaks are also there because the light field inside the cavity is actually a Gaussian. So you don't just have one mode, you have several modes, and these modes are visualized in this image with the respective transmissions. And there's this thing called the GUI phase inside of a resonator where you have an additional, the optical path length increases or decreases according to the mode of the Gaussian. So you can see that as the higher order modes have different effective frequencies that they resonate at. So you can see in my results as well, right here, you can see that we also have higher order modes. But in my result, you can see the fundamental mode, or the 0th order mode, is the most important one, which we're measuring, and we can measure the finesse of that and the bandwidth. And in my particular case, when you simulate the finesse of such a cavity, you see a finesse of around 4,500, which is roughly what I measured, a little bit less. And the bandwidth is around less than 5 gigahertz, which is 10 picometers. So if you want to make a spectral filter out of it, you now have a 10 picometer spectral filter in my measurement. But this highly depends on the reflective coating on these fibers right here. So if you have a higher reflective coating, as I mentioned before, this transmission spectrum will go even narrower. This transmission peak will go even narrower. So the finesse will go higher and the bandwidth will go lower, become lower. So you can effectively have much higher or much narrower bandwidths with much higher finesse. So this is the formation of a cavity with a broad spectrum light. And we can also measure the cavity's performance in terms of the length change. So I also measured that, which should follow the resonance condition according to the integer wavelengths, half integer wavelengths of light that I send in, and I sent in 780 nanometers. And what I do is I measure not just the transmission, but also via beam splitter the reflection that is coming. So when the light enters the cavity, it reflects off this surface, and then I measure that reflection, and I also measure the transmission coming out of the cavity on this side. And this reflection will tell me how much light was actually input into the cavity, and the transmission will tell me how much light was then further emitted into the cavity. And then the mismatch will tell us how much loss there is in the cavity. And that's what we measured. So the first measurements that I did, this is within one length of the cavity where the fundamental mode and the higher order modes are there. I have not shown the further length. But at resonance, at the fundamental mode's resonance, we see a strong extinction of light. So when we are at resonance, the light reflecting back is really, really less, about 2% of the light sent in. Not of the light sent in, of the background signal. And the transmission, the normalized transmission peak is corresponding there. you may question, because I was questioned this by one of the professors there, why is the light going more than 100%? That's because this reflection I'm mentioning is according to the background count that I'm getting here. The light I'm sending in is more than this. At certain lengths of the cavity, the cavity actually reflects more light than you get off resonance. And you can also see here. And this is according to this paper. You can also check this paper where the reflectivities and the equations that you make out of the reflectivities insist that the reflective peak is not a Lorentzian, but rather an asymmetric Lorentzian, where you can actually get a higher transmission at some point, a higher reflection at some point. So by fitting these functions, I can actually find the finesse and also measure the finesse, and that's what I measured. That's what I showed before. And then another thing is to check the stability of the cavity. So if you are at resonance, for example, you can look at the transmission of the cavity as a function of the length of the cavity. And any and if you go to a certain length of the cavity, so if you go, for example, at this length, the mouse is visible. If you go at this length of the cavity, you may see a certain transmission. And then any change in the system, in the hardware due to external vibrations may cause the transmission of the cavity to change correspondingly. And then you can measure approximate that linear change, and then you can compensate for that to lock the cavity at a certain length. And that's what we do. We send light in, we form the cavity, we measure the light, and then you see the change in the light. You can Fourier transform that change, and you can then send a correction signal via a piezo actuator into the length, into the cavity. And you can measure the change. Yeah, you can Fourier transform that change, and you can see what noises the system is susceptible to, the hardware, and also you can integrate that to see what is the total length deviation of how stable your system is. So in this measurement, for example, you can see it's like about half a picometer of stability. So the cavity length doesn't change more than half a picometer, or a little bit more than half a picometer due to external vibrations. So we see this, but the results are amazing, or at least I think they're amazing. I don't know what you think, but how does the hardware look like? Well, if you pull back the curtains, this is what it looks like if it loads. It's just two metal levers. One of this is here, the other metal lever is here, inside of which you can see the piezo actuator right here. And there's a foam piece on top, which is holding this fiber right here, going into this glass box right here. And another fiber is going into here, into this glass box. And this is just a wire connecting the piezo actuator. And this is just a metal piece that is onto which this thing is glued onto. So we just have glue and tape going on in the system. Do you have a question? Okay. We just have glue and tape and a foam piece pressing down onto it. So it's a very simple, whatever scrap material we can find, we use this to make our system. And yeah, this is the labels.
How big is it? I mean, won't it be difficult to take this whole system in some other hardware and put it in?
This thing is a millimeter.
Yeah, this is okay, but all the things like this piezo-enabled modulation device that you have is it the part of the setup?
So this is the part of the first prototype that I made. The idea was to just put the fibers in a glass ferrule and see if we form a cavity, what are the results with our fibers. And then the next step, which I will come to, will be about designing the mount to make it such that it is able to be integrated into a bulkier system. But that is one of the main ideas, that it should have open access, which this does not right now, and it should not be close to the cavity, it should be controllable. And here I'm showing a few degrees of freedom that I wanted to change. The first thing is to change the length of the cavity on a larger scale. The piezo can adjust up to like 100 or 200 nanometers, a little bit more, but up to like millimeters. If you want to change the cavity length, when I adjust the cavity length, you need a external system. So I have a micrometer stage onto which I have a lens tube that is holding a rotating tube, that is holding a improvised clamp system. And the rotating tube is to also be able to adjust the transverse angle of the two fibers. So the fibers are moving like this, but also I need to adjust this angle, the transverse or axial angle of the two fibers. And this is important because the profiles may not be exactly centered. So if they're a little bit off center, I might need to rotate to get them to face each other. Let's see. I will do that in a second. So another problem. So the first problem that we saw.
Will the axial rotation fix that? I mean, maybe you need another rotation about some other axis as well.
You mean these axes?
Yeah.
Yes. However, as I mentioned, when we manufacture these fibers, we actually cleave them really flat. What is the tolerance of the cleaving? Like it's about nanometers, I would say. Around a nanometer of tolerance of cleaving.
So as far as you're concerned, if you just get this axial, then you're good. Okay.
So, I mean, if you want to get this sort of rotation,
No, I don't want it. I mean, the question is it needed or not? That really depends on how you prepared the thing, right?
Some other applications actually do that. The Tracy group, they had these lever systems because they wanted to do this, but then you need complication.
Absolutely.
Actuators.
Yeah. Right. If you can live without it, then no need to go for that.
So everything was good in the first half, but then what are the problems with this system? Well, the first thing was performance range. So when I do this measurement that I mentioned earlier with the transmission and the reflection, changing the cavity length and going over it, I see how far does that cavity perform and how much light does it transmit. The transmission of the light was very important. And so here is a measurement that I did with the first set of fibers that I used, where you can see the transmission of the light and also the reflection. This is the fundamental mode, the Gaussian, and this is the higher order mode of the Gaussian that I showed before. Same here with the reflection. And you can see that while the reflection really extincts at certain cavity lengths, the transmission is hardly 1% of the light that I sent in. So this was a big trouble that we saw. And the second thing is that the radii of curvature of the ablation profiles that I had were up to 200 micrometers, 150 to 250 micrometers. But according to simulations, the cavity should perform up to this length, 200 micrometers, but I only perform 40 micrometers. This was a question, why does this happen? And I mean, I have a lot of other graphs about simulation that I don't want to bore you with, but when you simulate the cavity length, it's like, should be 200 micrometers. You can also look at the beam size. Okay, maybe the beam size is too large at certain lengths, such as of the Gaussian right here. At the mirror, the beam size may be too large so that it doesn't capture the fiber core, doesn't capture the light. But when we measure all of this, this should not be the trouble. This should not be a problem. So then what is the problem when we were questioning that? When we measure the finesse, however, it also drops down to 40 at 40 micrometers. So then the question is, it's definitely the mirrors themselves. It's not about the beam, it's rather the mirrors. The mirrors may have some limitations in them because the finesse only depends on the mirrors. The finesse only depends on the reflectivity of the mirror or the end facet of the fiber. So what would be the problem with the fabrication? But the first thing, as I mentioned, when we laser ablate the fibers, the profile should be at the center of the core, but it may not be at all times. There may be some deviation of exaggerated effect here. And this deviation then may cause something like this, where the Gaussian that forms does not overlap with the fiber core that well. And another trouble we can have is, as I mentioned, the cleaving. While we do have a tolerance of a few nanometers, maybe it's not that, maybe it's a little high. And so again, I mean, I've drawn a cartoon here, it's not simulated data, but the idea is that also it may not align well with the fiber core. So one thing we tried with this same fiber set is that we try to rotate them, as we discussed just now, because the core might be here, but the ablation minimum might be a little bit off-centered. And so we measured that, but it did not make a big difference. The reflection does seem to go down, but the transmission maybe goes up to 1% from 0.5%. Not a good result. So what can we do? Well, we had these requirements. We met some of them. We did not meet some of them. And we also had some trouble with the prototyping system with the glue and tape, where I hope this video works. Where if I change the cavity length, for example, so this is the transmission spectrum from a spectrometer, and I'm changing the cavity length in the microscopic image you can see. And if I manually move it, as I mentioned, I had the stage, I'm moving it with my hand, the system just drifts away. So I have a very low precise control over my system because it's just handheld right now in this first prototype.
What do you mean by drifts away? What is that?
So what I'm doing here is just moving it with hand by a very small amount. But because first of all, it's on a stage that may not be so precise, but more importantly, it's clamped really far away from the actual cavity. So it sags a little bit. And so if you push forward, the fiber may sag a little bit and then move forward, or it may pull not so nicely.
Yes.
And fine control is very important. If you want to have a measurement and you want to transmit in only one band, if your system just drifts away, what's the point? So whatever we do next needs to be more precise. So we did a proof of concept, but what's next? Well, we have a second generation now. The first idea is to select better fiber mirrors. As you mentioned, we did not have good results with our current fiber mirrors, select better fiber mirrors. Second, try to make it open access. We need to put something inside the cavity. We don't just want it inside of a glass box. So maybe cut open the thing as the other group also had. And the third thing is to make a rigid and precisely manufactured mount so that you can precisely move the system back and forth. So to see if we can actually do this. And second is to clamp from both sides. We right now only had a sagging system, but maybe have it attached perfectly. And on the front of making it open access, we can also perhaps have two ferrules facing each other. And the idea is it will be passively aligned with here, but we can have it inside of a flexible mount. So what you can see here is a metal piece underneath, on top of which another metal piece is mounted, which has two of these sort of flanges, I would say. And this thing is bendable. If I push through with a screw, for example, it can bend the material. And then I can actually transversely align it, as you asked before, whether I can align the two. But that might be the solution to off-centered profile. If you have an off-centered profile and rotation doesn't make a difference, maybe if you slightly move it, maybe you can slightly make them face each other. So this would be up to like 10 micrometers or so at most of movement. And the third thing would be to use a better positioner. So this is, I mean, it's a complicated image, but this is a Colibri manufactured flexure-based positioner that can use a piezo to amplify the movement so that you can move up to 400 micrometers of movement with just a piezo. You can use lever systems to amplify it. So maybe you can remove the handheld part of the system altogether and do it. So this is what we tried, the two designs that I showed, this one and the other one, and I'll show you the results from it. So the first thing is that when you rotate the fibers, we used new fibers, we used better profile fibers, and then when we rotated them, then we can see that the transmission actually goes from 0% almost up to 7-8%. So there was an improvement with better profiles of our fibers, and the reflection also extincts. The reflection also extincts down with different lengths. And then I did a bit of a statistical analysis with different fiber mirrors to see whether the ablation profile or the size of the radii of curvature makes a difference. And actually with up to 60 micrometers, if we use fibers, you can go up to 35% transmission. So transmission went from 1% to up to 35%. So if you want to make a filter out of it, or if you want to have percent enhancement, you can actually get high transmission, I would say, still higher than before. And this new design that I mentioned with the bendable mount, I also did the proof of concept of this. Well, it's very hard to see the difference because the change in the transverse displacement is very, very low. It's up to a few microns, but you can see the difference in the transmission. This scale is actually 35%, and this thing is 5%. So the transmission goes from less than 1% to up to 30% with just a few microns of displacement of your fiber. So the idea was to get a mount, try to see what are the different solutions to getting a better transmission, and whether we can make it open access and still have good transmission, good performance, and good stability. And this is where my project sort of stopped, because the company was also looking towards other customers to see whether they are interested in buying. And at the moment, the project is in the gray zone. They're still thinking whether we can make a product out of it. But they learned a lot in what we can do. We can use our current profiles in our fibers. We can make an open access mount, and we can finally displace the two fibers. So with that, I'll quickly conclude my talk. So the idea was to make a quick proof of concept. And what were the results? Well, we got less than a picometer stability because of our passive alignment, because of the fact that the fibers are inside of a ferrule. We got up to 35% transmission power of our fiber cavity. But unfortunately, we only had up to 40 micrometers of stable cavity range. So this is the next thing to look at. How can we prove this? What is the matter? Why isn't the cavity performing more than 40 micrometers, even though we have profiles up to 200 micrometers? And the idea or the problems would be that the problems that could be causing this is the mode mismatch. So either the mode is too large at the mirrors, or the mode is not aligned to the core of the fiber. So you would have to go for better cleave angles and better concentricity. The core of the fiber should be at the minima of the ablation profile. And we did some proof of concepts with future designs with either a fine control with clamping mechanisms or with fine alignment by bendable mounts. And we showed that this actually works. And we can fine align fibers and we can make an open access cavity. But future efforts would be to do what you mentioned, which is not have so much material around the fibers, to have it more close. But the further away you keep the fibers from a clamping mechanism, the more mismatch, the more, I would say, slack or the deviation from alignment the fibers can have. So that's the trade-off of what you can do. And with that, I would thank the Fabry team and thank you for your attention. I'm open to any questions.
Very good. Right, so does anybody have questions or?
That the project has stopped. Are you still working on that?
This was my master's project and I finished it. I wrote my thesis. So now it's up to the company whether they want to continue with this product. As far as I know right now, they are, because it's a company, so they need to look at customers. So I think the customer interest wasn't extremely high at the moment. So they were like, okay, well, we will pause this for now, but we know whether we can do it if we need to. We have some designs and some ideas.
You can further refine it, right?
Yes.
You have the ideas to that.
Yes. We did a proof of concept.
And how expensive is it? I mean, if someone wants to implement it like in the lab and then use it, for example, how expensive and how complicated it is to.
I mean, I don't work with the sales at all.
Yeah.
Fancy does a little bit, but she doesn't work with the money part of the sales. But I would say, so QDB's current system that they actually.
Well, the thing is, you hire him and you have him make it. That's gonna be cheaper.
Accessible is I mean, for people in their lab, how accessible this instrument?
I mean, people usually get funding to buy the current systems. Like they can go from a couple of €100,000 to 20,000 euro, 200,000 euros or something like that.
I told you it's cheaper to hire him.
I will not charge you €200,000.
Yeah, we're not paying.
I was hoping to sell you something here. But like if you make so it depends on the product. If you want a filter, you don't want it open access. You don't want a lot of complicated systems. Then it may go up to 10,000, 12,000 euros. But if you want to make like a whole ion trap system, then it might go up high. But I don't work with sales. I would not know the money part of it.
Right.
So if you are working in like a pump probe system with that, like send something in. If I look, for example, shine a 50 nanometer on it.
850.
For example,
Yeah.
and when it's scattered from the whatever the thing is, and it fluorescent some light, how much the resolution, like it if I enter 850 and it emitting 50.2, whether it will differentiate that the cavity.
The cavity.
Can it differentiate that two node that closely align? Like if I say in a frequency range, can it differentiate between 2 gigahertz photons?
Depends on your line width. If you have a really narrow line width, which is like the 0.1 nanometers that you mentioned, if the line width is even thinner than that, then you can filter out either of the two wavelengths. If you have two emissions within 850 and 850.2, for example, but then it depends on your line width.
But what detector you are using at the end? Like it's just a cavity. Like if we have a Fabry interferometer, that is a big setup. So what is that? It has a big cavity system. So when one mirror is fixed and one is continuously moving.
Yes.
So we can differentiate different modes coming at the different, like length is changing, so that the resonant mode is changing. So it can differentiate between the mode, you can say in a megahertz range, like 199 megahertz. So how much it can resolve the two photons? That's my question.
So, I mean, the finesse that I used here would be like gigahertz. It wasn't megahertz, but our customers did demand like a megahertz resolution. But I think you're asking in terms of length deviation, like if you.
No, we are using in a length, but whatever system you whether is the length or is the reflectivity, the maximum range what you achieve with the resolution, like you are saying in a gigahertz range you can differentiate to photons.
With my current finesse, but if you have a higher finesse, then your line width goes thinner. And so you can then differentiate more. But you're talking about are you talking about spectrally or are you talking about in terms of length?
No, whatever the parameter maximum range your system has. Like it can work in a gigahertz. Whether you change the cavity or fineness or whatever, you can differentiate with the photon in a gigahertz range.
Yeah,
that will be in 100 of gigahertz maybe.
No, it's like 5 hertz
at the moment. 5 gigahertz. Okay.
Megahertz should be possible if you have thinner line width. 100,000 finesse, 150,000 finesse. We have really high finesse in these small microcavities, 150,000. Another group, I think Hunger group has 300,000 finesse, which is very high.
I have another question, just technically, like you were saying, when you twist one of the fiber, if two fiber are like that, if you are twisting it like that, how it will go like this? Like in one of the system, you are just rotating the axially.
Yeah.
So how, if you whoever are like that, if you are rotating in about it, it means the system you are prepared, like there is some tolerance in it, it is not fixed. So it means there is something you need to.
In the laser machining, when we make this machining, the machining may not be exactly centered to the fiber core.
Okay.
I mean, it's still micrometers, but that can make a big difference when you make two fibers. If you have a big mirror, on the other hand, that QDB already does, then you don't care about that because the big mirror doesn't have a core or the whole mirror is the core. So you can capture light wherever. But if you have a fiber, then you need to make sure the light goes into the core of the fiber. And then you need alignment. So this rotation, the idea is that if you have a bit of a mismatch, you can rotate it to bring it here.
Okay, you are completely rotating not just around one axis. You are just rotating it like that, not like that.
Like this, just around one axis.
Yeah.
But on this end facet, if the fiber is a little bit misaligned, you can rotate it to bring it here.
Okay.
It's a little bit misaligned. And then the two ablation profiles can face each other. Welcome. I guess I'm available for informal questions afterwards if you want, but I will give it to Jonathan, who's been waiting very patiently. So thanks a lot.
Super impatient.
Super impatient. There you go.
And maybe give it.
Yeah.
So transfer.
Yes, but I think I'm sharing only one window. Change the sharing. Keep sharing, share again. Share the link presentation. Now should be.
Even full screen.
Yeah, you can try. My laptop is a little slow, but it's fine.
So a little bit of a switching topic. We're still like tangentially in stuff like fibers. So I just wanted to give you maybe. So I have this company called Linque. We come also out of LMU, good friends with the Curie group. And what we do is we work in integrated photonics. And I thought, because I didn't know the audience that well, I give you basically a little bit of a overview about how integrated photonics works, what it is, and what we want to do with it on a more basic level. So just before I the first thing I want to start with is what is integrated photonics. So we talked about optical fibers all the time, and how an optical fiber works is basically you have a core of glass which has a certain index of refraction, and you have a cladding around it, which is a different index of refraction, which means that you have, at least if you go straight, have a total internal reflection, which means that the light is confined in between these inside this fiber. And what you can do now, you can put the same principle onto a planar chip, and which is then similar to a normal integrated circuit. So in this case, the basics, which is called silicon photonics, is you have a silicon on insulator wafer, which is a silicon substrate with silicon oxide on top, and then a thin epitaxially grown silicon layer, and then you basically etch a waveguide out of it, which is like a few hundred nanometers across and 220 nanometers in vertical height, and you get the same effect. You have a very strong index or a very high index of refraction in silicon and a lower one in silicon dioxide, and you can confine a light mode, of course, in a range where silicon is transparent, which is typically in the infrared range. So, for example, 10 nanometers or 15 nanometers. And on the right side, you basically then see the simulation of how the mode profile is. And on the bottom, you see a microscope image of how this thing is being made, or like how the structure looks. So it's basically you etch away, and then you have this waveguide in the middle. So integrated photonics suggests that you build circuits. And if you want to build circuits, you need more components than just a simple waveguide. First component you need is something to put the light onto a chip, right? You have to chip how to get light from a laser there. And the easiest thing to do is a so-called grating coupler, which is in a simple way just a grating. Grating you can use to cause interference, and you design this grating in a way that if you shine a beam of light, for example, from an optical fiber onto this grating, then the interference is such that the light gets guided from the vertical to the planar and into the waveguide. And depending on how complex this is, this can work really well. In like the more like if you just use one layer, then you have a transmission or have a loss of like 5 to 6 dB, which means that you get like 10-20% into the chip, which for some applications is good enough. And in extreme cases can be down to like 3 or 2 or even 1 dB, which means that like 70 to 80% of the light gets actually cut into the chip. Then the next basic object or basic component that you need on a chip are so-called multimode interferometers, which is a way to like couple or split up different waveguides. It's also actually like when you build it a fairly simple device. It's just a box that is made of silicon, right? You can see the contrast, what is silicon and what is silicon dioxide, which allows the beam to basically be split up or combined. And if you go into more detail, it's actually quite complicated because if you see the simulation down there, what you basically do is you interfere in multiple modes of the light because you have a higher mode volume. That means you can not just a single fundamental mode, but all the other modes have into this volume, which then means that you have to precisely design the shape or the length of this box such that you have maximum intensity in the two output waveguides, or if you like mirror it from the two into the one output waveguide. But this is basically how you can split up and combine signals. This can be also done with something that is called the directional coupler, because the waveguide, the mode is confined into the waveguide, but it is also living slightly outside of the waveguide. So if you bring two waveguides very close together, the mode can basically wander from one to the other. That means if with a certain length, you will get a certain splitting, right? Like if you imagine light coming in from one side there on the left side, and then you have a certain interaction length, and then when the two waveguides diverge again, you will have a certain ratio of light in one or the other, and then depends on the length, and it also depends strongly on the wavelength, right? So if you have a slight shift in, for example, the length, then you will get a completely different splitting ratio. So now you have some basic components, and the question is how you can tune it. The most important tuning element in integrated photonics is a so-called phase modulator, and you might know it from like also as a macroscopic object, like these electro-optic modulators that from Thor Labs or whatever that you use for modulating macroscopic fiber-based or even fiber-based lights beams. And in integrated photonics, you basically have two different approaches to that. One is the so-called thermo-optic phase shifter, and one is the electro-optic phase shifter. The thermo-optic phase shifter is very simple. You just put a little bit of metal filament above the waveguide, and if you run current through it, it heats up, which means that the waveguide heats up, and when the waveguide heats up, the refractive index changes slightly. And if the refractive index changes slightly, get a phase shift, which means you can modulate the light through the heater current. So the advantage of that is that it is fairly simple. It has a very low optical loss because it basically just smoothly changes the refractive index. There's no interface. But the drawbacks is that you need to heat it up with constant current, which means that you need a fairly comparatively high power consumption, and that it is slow. And slow in that case means it's on the order of up to maybe 100 kilohertz if you're lucky, or if it's perfectly designed, but definitely on the order of microseconds to tens or hundreds of microseconds. So if you want to do faster modulation, and this is what's typically used in sort of communication applications, I can come to what that means in a bit. Use electro-optic effects. The most mature version of that is the so-called depletion phase shifter, which is essentially building a diode in the waveguide, right? So the PN, where the PN labels are in the middle, this is essentially the waveguide, and it has like these wings out to the side. And if you apply a voltage between them, you create a depletion region in the middle because it's a PN junction, and that slightly alters the refractive index as well. So this effect is very small, right? Like, so these phase shifters, if you want to have like a high phase shift, which means full range until basically the waves overlap again, these can be like hundreds of microns or even millimeters in length. And like in some, if you build it like for example, as a transmitter for optical signals, you can basically have one chip of this size, and like the whole length is the phase shifter. But they're very, very, very fast and very mature. So like currently the foundries are working on getting those like mature enough at a modulation frequency of around 100 gigahertz, which means that with like certain modulation formats, you can get like 400 gigabit of transmission on a single wavelength channel per second. So now, the first more complex component on integrated photonics is so-called Mach-Zehnder interferometer. And this is sort of the first thing where you can actually program certain interactions between the light onto a chip. Mach-Zehnder interferometer is a fairly simple construct. You have, and you probably all heard it in the physics lecture, you have a light beam and you split this light beam up and you combine it again in another beam splitter, and then one arm you introduce a phase shift. We know what the phase shifter is. We have talked about it. The beams are just the waveguides. So if you take waveguides, two multimode interferometers, and then some phase shifters, you build a Mach-Zehnder interferometer onto a chip. And this is essentially how it looks like if you use it, right? Like, so these are thermo-optic phase shifters on top. So basically just very narrow metal wires. Narrow because then the resistance gets high, so you dump all of the power into that specific area and it heats up. And then the output splitting ratio, you can see basically the tuning of this of the Mach-Zehnder. So what do we want to do with it? So do you see the title there? This is computing and integrated photonics. So what we want to do is use this for computation. And if you want to use something for computation, you do a mathematical description of it. And the Mach-Zehnder interferometer, if you just write it out in math, is essentially a matrix multiplication of a unitary matrix onto an input vector, which is encoded in the intensities of the two inputs. That means this parameter phi there, if you tune that, you can basically create an arbitrary unitary matrix to be multiplied onto the input vector. And this is the basic building block of how to do actual like big, large scale matrix multiplications in integrated photonics, because out of these 2x2 matrices, you can build larger matrices, and then with a large network onto a chip, you can build sort of a computer. Yes, just a little bit, because I'm always conscious about not having enough math in my talk. Another formula, because if you have a unitary matrix, you of course can't, by itself, it's not an arbitrary matrix, but you can construct any arbitrary matrix through the singular value decomposition into unitary matrices and a diagonal matrix. Unitary matrices we have covered already. And for diagonal matrix, you can just have one input, one output, and then use the MZI as an attenuator, right? Like you dump all the intensity you don't want into an unmeasured output. So you get basically a factor smaller than 1 onto the input value. And then for this you can do for any of the diagonal inputs. So you need one MZI per diagonal input, then you have a diagonal matrix essentially. If you have questions, ask.
So how good is the accuracy of these machines? I mean, how good? I mean,
so that depends a little bit what you shoot for. Like, so this is analog computing,
yeah.
Right? So short answer is we got it to 8-bit precision. Longer answer is the question is to think about what you need it for. So the main application for that is AI. Let's say the main application where it is being targeted towards being used is AI. And in AI, you need a lot of matrix multiplications. But the good thing about AI is that you need fairly low precision, right? Like, so even in like the digital accelerators, you use 8-bit, you use sometimes even 4-bit precision. And in that case, it works perfectly. There's also a different sort of more theoretical background where, at least in sort of the electronic realm, where you compare analog to digital, at least for AI accelerators, is that there's sort of a the performance of the analog system would be best when you have low precision. The higher the precision, the better the digital one gets, or in comparison from, especially for the efficiency and the power consumption and stuff like that. Because the higher precision you need on an analog system, the higher your signal strength needs to be with regards to the noise, because you have to resolve all these different steps. So the analog system is best when you have low precision. And that's why we never tried to go beyond 8-bit.
Right.
Yes. But this we achieve.
Okay.
And this is also like, this is not that big of, this is not so complicated, at least for a single matrix. Tuning the big matrix, different story. But for a single, like a 2x2, this is fairly straightforward.
No, but
there's also certain like there's imperfections in the fabrication of these. And that means that the extinction ratio doesn't get arbitrarily high. So you can't completely get to 0. And this is maybe, depending on how you design it, like 10 to 20 dB damping on, or like extinction ratio. And I'm always struggle to go between dB and percentage. But
right.
So this is not a problem for 8-bit, but at some point this gets an issue as well.
But okay, so you get good precision with a 2x2, but let's say for real matrices, can you? You
can replicate it. 8-bit is definitely doable. 16-bit is.
No, I mean 8-bit is fine.
8-bit is fine.
If you can get.
Yes. But then the question is also how stable it is.
Is the advantage the speed with which you can do things over here?
The speed and the energy efficiency, because the cool thing about this is that when the matrix is programmed, the computation itself doesn't really consume any energy, right? Like you just send the light in and get the light out. And the computation is basically done passively because it's just going through the system. That means the only sources of energy consumption are basically having the system programmed, of course, and then encoding the signal into the light. And that is basically just scaling with the vector size, right? You need digital analog converters and analog digital converters on the inputs and outputs. And while sort of if you build it up, like build all the elements and all of them have to be like faster and better, it scales like quadratically. This trade-off is not always in the favor of this type of system. Just to make it short, right? Like, so if you look at the literature, like a lot of people have worked on this, you typically see people reporting one measure and say it's really good and ignore the other, or do it the other way around. So in principle, if you ignore all this encoding or do it like really, really slowly, really energy efficiently, then you have like femtojoules per bit, which is like orders of magnitude better than an electronic system. But if you then on top of that want to like 100 gigahertz encoding speed, then you need like really energy intensive encoders. And this can work in favor, but it's not like a slam dunk.
Okay, very good. Thank you.
But yes, so this is now a system that we actually built, right? Like the picture you already saw in the beginning. This is the sort of the layout, right? Like this is actually what's used to fabricate the chip. And you just have a network of these Mach-Zehnder interferometers, plug them together, and then you can make your computations. And all these red dots are the input couplers, where you then take a fiber array. The fiber array you see in the picture, which is just like a bunch of optical fibers in a V-groove array, so basically just aligned next to each other. And then you couple them all in at the same time and all out at the same time and do computation. Yeah, and like this is the first thing that we did at the time when we got it running, which is sort of a little bit of a toy model for image filtering. So you take this Super Mario image and transform the color values to like highlight the pants. It's not that impressive compared to others, but we were happy it works. Okay, so something that we currently are a little bit more interested in, actually, which is more near-term relevant, is so-called switching, right? Like because if you think about it, you have two cases of matrices in this matrix computation that basically correspond to just keeping the vector as it is, or just flipping the values from one to the other side, which is essentially a switch, right? Like if you have a signal going in and you want to have it on this side or on this side, you can use it basically to switch those signals. And these are converted as like the cross and bar states, right? Bar because it goes like a bar, and cross because crosses. Mm-hmm. And this we also then with the same system tried. So you can basically have a signal coming from one side, and then in each of the elements you can decide, does it go one or the other way, and then you can basically project it on any of the output channels that you want. And then you see the result of that switching on that side. It's not completely perfect. We have better data now. I haven't included it here. And what the graph means is actually is essentially like the rows are the target channel that you target, and the columns are all the photodiode outputs, or the other way around. And the diagonal basically means you can like tune the system so that the light goes to the output that you want to, right? Like if it's off diagonal, then it goes to an output that you don't want to. For example, in this bottom right half, there was one of the drivers for one of the MZIs was broken, so you basically couldn't tune that channel. So
you're adjusting the thermal
yes
switching at every step, and then you want to target a channel.
Yes,
but the signal may then go on to a different channel, and you see the fidelity of that.
Yeah, but like if you have one of, in this case, I think this was this MZI there at the bottom, a little bit to the left. This was couldn't be addressed because one of the op amps on the driver was broken.
Okay,
which means that it was just random. Okay. So there was a limit on how much you could tune it. Yes, and as I said, this is a little bit more interesting because it's actually used in industry. So optical is so-called optical circuit switching, and this is used in data centers as a way to replace, at least partially replace, Ethernet switches. Because an Ethernet switch for optical fibers in a data center can consume on the same, it's basically a high-performance computer, right? You have an ASIC chip inside that consumes like a kilowatt for like 100 channels of light, which means that the communication, including all the transceivers, basically the transmitters and the receivers that transmit the electrical signals onto a light signal, now consume in an AI data center at least on the order of 20% of the complete power consumption, right? Like, and this is wasted power consumption, right? You want to use it to put in your GPU to do more model computation. So you a lot of companies, the first one was Google, were looking into how to minimize sort of the communications power overhead. But so far, those people have mostly deployed free space solutions, right? So essentially, you take an optical fiber and then you project it onto a micro mirror, for example. Different ways exist, and then that micro mirror shoots the other fiber, and then you adjust these mirrors to assign which fiber goes into which fiber. These are very bulky systems. They're also not completely energy free, but and they're also very slow, but they are very very low loss, and this is how they're being used. Just to say why the integrated approach would be interesting, because these, as I said, are very slow, so they adjust at best on the order of like a few milliseconds or tens of milliseconds, while even with the thermo-optic phase shifters, you can, on an integrated chip, basically switch on an order of microseconds already. And with better phase shifters, which we're also developing, you can then go to the nanosecond range and do really, really interesting new type of switching. Okay, yes, this is our team. Thank you for your attention.
Very good. Thank you.
Any questions?
Good.
Good. Either everyone understood everything or nobody understood anything.
Yeah.
One of the two. So you decide.
I just
Or some people
choose to
understood
believe.
Everything and some people didn't understand anything.
Perfectly valid.
It's not their fault.
The distribution.
I'd like to think that I understood everything.
Nice,
Okay.
nice, cool.
All right. Yeah, so no, this thing about switching is very fascinating.
That's why we do.
It just brings me to my undergrad degree, where I never got to do a course on optical switching, but it was there in the outline.
Okay.
One class, which wasn't offered. So
Oh.
it's sort of,
Brings it back.
it brings back memories of,
Yes.
I wish that had been offered.
Yes. I mean, optical switching and in general, like integrated photonics, is actually not that young. So there was a big.
Yeah, I'm fairly old.
That's not what I was saying. But I mean, like it was a big hit in the early 2000s. Yeah. And there are some companies like Infinera or so that are still going from that time and are now being bought. But for this computing and for the switching, the technology just wasn't far enough. Like people were doing it in a lab, also with glass circuits and stuff like that. And then people mainly focused on transceivers. And transceivers are very mature, right? Like these silicon photonics, these depletion mode phase shifters being used in transmitters and receivers. This is mass produced, and basically every of the transceivers used for data centers, like these 100G, 200G per second transceivers, are using these type of chips. But it's very simple chips, right? Just a transmitter and a receiver, like a photodiode, for example, germanium photodiode can be integrated, and like a light source, like a laser, external laser, and one of these phase shifters, and you have a transmitter. And they're very cheap to make because it's silicon. But sort of the challenge for us and why we are a startup and not a robust company is that these big chips are have a lot more technical challenges to make.
Okay, very good. So questions, comments, and I understand that you guys are going to stick around for a bit if the students want it. If you want some guidance, perhaps on admissions or whatever, or you just want to have a bit of a chit chat. So please feel free. These guys are kind enough to say that they will.
Kind enough to say.
They'll help you out whatever way they can, at least for today. All right, thank you.
Thanks a lot.
We can